Singh. Upkar has been working on broadly in the topic of visualization in oceanography, and specifically has been looking at this problem of tracking salinity and features corresponding to that within the ocean. So Upkar got his master's from NIT Calicut, and prior to that, he got his bachelor's from Jalandhar.
Guru Nanak University.
Has been working on his PhD since then. Over here.
Okay. So today I'll be talking about feature tracking and visual analysis in temporal scalar field, specific to ocean data. So why is it necessary to look at these fields? So in many fields of sciences, especially geosciences, to understand any type of phenomena that's happening around, we need to basically collect a lot of data, try to understand it, visualize it, maybe try to track some phenomena in there, and it basically requires you to start with collection of data, which is basically either done through satellites or simulations or reanalysis, where you take some real life data, collected data, and pass it through simulation and do reanalysis. Click something. Might have clicked something. Yeah. So we basically focus on the same problem, similar problem, specific to oceanography, and we try to design methods that can help us track some scalar fields in some features in temporal scalar fields. And the methods we introduce are general methods, which could be used basically, in other fields also. We, you know, we saw this problem basically from Bay of Bengal's perspective. So in oceanography, we consider salinity as, in PSUs, which is just 1 gram of salt in 1,000 grams of water. So Bay of Bengal actually has a lot of fresh water coming in from all the river systems it has, and the average salinity of Bay of Bengal still remains same. We can see here on a plot that the salinity values near to the coast of Bengal are basically low. Fresh water is generally considered at 0.5 PSU, and that's what we get as inflow into the Bay of Bengal, right? But still the average salinity is kind of fixated at 35, which is considered high above 35 is considered high salinity. So where does all that salinity comes from? A theory suggests that we have summer monsoon current to thank for that, and it starts basically from Arabian Sea and brings high salinity water into Bay of Bengal through, near the east of Sri Lanka. This is where it enters. So we can see a little bit darker shade here, which shows there's a salinity a bit higher here. And we have existing theory which says that starting from this point, which we call high salinity core, where PSU is greater than 35, greater than equal to 35, the water gets high salinity gets pumped into the Bay of Bengal in form of cycles over time. And we wanted to show computationally that how that salinity starting from high salinity core gets distributed throughout the bay. There have been existing studies like this where they track some sort of scalar field in oceanography. This is important because studying this some sort of scalar field can give us information on other scalar fields, how they move. For example, we have studies about how heat movement in ocean affects the movement of ice and other things. We also have studies that show currents switching their directions due to weather patterns or things like that, and they act like basically railroad switching, like moving. First they are moving towards west, and then after some weather they just start moving towards east. We also have some studies in oceanography that basically use identifying certain phenomena and then tracking it over time to basically understand how things are affected by it or how that particular phenomena behaves over time. Uh, for this, we have one thing which is majorly used in oceanography is temperature salinity diagrams. These are used to basically detect a water mass, uniform water mass, which they then track over time. And there are also, some studies which focus on a specific phenomena. For example, let's say you want to track a cyclone. So you start with the definition of a cyclone, and then extract it out of data, and then you track it over time. We also have similar studies from computer science visualization background where they use topological or geometric features. For example, we use isosurfaces and isovolumes. Isosurfaces are basically uh, you can call it a pre-image, or basically it's a surface made by collection of points with a single exact value. And if you collect a bunch of isosurfaces over a range of values, you get an isovolume. And there are studies that use these isosurfaces and isovolumes to track some sort of topological feature from a data set over time. We have merge trees, contour trees, and reap graphs, which are basically dependent on such isosurfaces and isovolumes and help track some features over time. We also have something called a tracking graph. Tracking graph is basically uh, you take either one of these features, merge tree, contour tree, or isosurface or isovolume, and you create a graph in geometry and see how things actually move physically in space over time, or how their shape evolves over time. Uh, so we also have some specific studies in visualization where they just want to study the geometric features or topological features of a data set. So we see that most of the visualization studies focus heavily on either geometric or topological features and then try to understand the data using that. Uh, Specifically for visual analysis of ocean data, we can do something different also, where we can just basically manually push the data into some visualization tool and just study it over time, how it actually moves or evolves by taking some snapshots or recording some videos out of it. But well, that can be challenging because you won't get very deep understanding of data from that. You can get a cursory reading of the data using that for sure. Major challenges in this kind of study are, well, one of them is growing volume of data. So this basically comes up as a computational challenge because as the data sizes increase, as we have more and more computational power, we can do better simulations, or we can collect better data through sensors. Even sensors improve over time. So as the large data size grows larger and larger, existing solutions need not work for that data set size. So we need a system that's scalable, that can work better on larger data sets, and which can deal with uh, with growing sizes of data over a certain domain. Another one is lack of physical features. Like I said, there are some studies which focus heavily on, from ocean science, which focus heavily on starting with the definition of a phenomenon or a physical feature that they want to track over time. What if a data set doesn't have a feature like that? What if you want to look at something different, which doesn't have any feature, and you will have to come up with a definition? So studies where we don't have physical features, that is another challenge. There are some options where we do have features, but they drastically evolve over time. Our high salinity core is, one of the examples here. It starts as a packet, but then it starts evolving its shape and size over time, and so you need a definition that can consistently capture that evolution of shape or its size over time, and then consistently track it. So these are basically computational and representational challenges we have. And like I said, visualization community focus heavily on geometry and topology, and in oceanographic community, we basically focus on extracting some features that already have fixed definitions. Uh, cons- uh, Using these exact solutions that already exist doesn't fit, because we don't exactly have a what do you call, a feature definition that we can use here. And the geometrical and topological solution that we have from ocean science, oh sorry, from visualization community, they well focus heavily on iso surfaces or iso volumes, and then extraction from that. And high salinity core cannot be, we can't represent a high salinity core using an iso surface. We could do it with iso volume, but like I said, with growing size of data, that would become a problem if you have to track the whole volume of data over time. And the oceanography solutions are all or more or less restricted to a certain definition, a certain feature. So you can't exactly use it in a general scenario. So we wanted to come up with a, system or a framework that is robust enough to be used over different scalar fields and track them over time. So that was our problem statement going ahead, to come up with methods and frameworks to track and visualize scalar fields over time. Uh, the major challenges we would deal with, I guess, is one, like I said, HSC evolves over time a lot, and we need to capture that. And another one is growing size of data. We need to be able to handle larger data sets as they keep growing over time. Uh, the ma- so the methods we introduce and the data sets we use for basically testing or doing case studies for these methods. We use three major data sets. One comes from NEMO, which is 1/12 of a degree across lat long and 200-meter depth, and we use 122 time steps. That's the size of data. And we use two other data sets. One is global reanalysis, which is same size, and we have a ROMS dataset which has a higher resolution, which is 1/96th of a degree. So 1/96th of a degree basically goes around a kilometer in length, and 1/12 of a degree is roughly around 10 kilometer in length. So yeah. Major contributions we did through this work is, one, we came up with a method which we call front-based tracking method. This extracts features from HSE and track them over time. This is a parallel method. We'll show how it helps in speed up and how scalable it is. We also introduced another method which is based solely on advection, which shows how the movement of salinity or a scalar field would happen just due to advection. Uh, Another one we did was scalable implementation or scalability analysis of our data, of our methods. And like I said, this is more or less to show how parallel our methods are and how scalable they can go to a larger data set. And then we present this implementations of our fast implementation or parallel implementation of our method as a simple filter for use by domain scientists without with a user interface. So I'd start with front-based tracking. So what exactly is a front, or why exactly front? So when we look at iso volume of the high salinity core, which is greater than equal to 35 PSU, we see that it actually starts uniformly, and then it splits into multiple shapes. So HSE keeps evolving over time. And if we just look at the right side, which is just the boundary of that high salinity volume or high salinity core, it shows us basically similar shape. And we can see that just looking at the boundary surface of high salinity, we can get same results if we want to look at it. So like I said, if we had tried directly through iso volumes, that would have well done the job, but it will just increase computational uh, overload, right? So we can just focus on the boundary which is moving up towards north, and that will be enough to see how this high salinity core moves. So we call this surface or boundary surface of high salinity core, which is facing north, as a front. Okay, so it's basically the front of high salinity core, and we call our method front-based tracking method. So it's basically overview is you extract that iso volume greater than equal to 35. That basically gives you a coarse representation of high salinity core, and then you extract its north-facing front, north-facing boundary, and then you want to track that over time. That north-facing boundary, I would use the word surface front for it from now on. So we'll just call it surface front, and we want to track it over time. We so to track it over time, we need some sort of connection between, let's say, two surface fronts over time. And for that, we use a neighborhood. This neighborhood comes from basically the current's speed from Bay of Bengal. Like I said, SMC is the current that brings high salinity water into bay, and the average velocity of those currents in bay comes around 70 kilometer a day. So we create a neighborhood because we have temporal data of 1 day resolution. We create a neighborhood which basically 70 kilometer radius over 1 day, because we will extract surfaces over 1 day. Over two times which are 1 day apart, we need a neighborhood of 70 kilometer, because that's the maximum distance any current can travel in this. And we define this neighborhood basically for a single depth step just as a 70 kilometer radius circle. And to go into 3D, which I'll just call N3, we'll take D minus 1 and D plus 1 and take a union of all of those three. So that's how we define N3 neighborhood. N2 would just be in that particular depth slice. Okay. So how do exactly we extract surface fronts? One thing, all the computation is basically done, is basically independent of each depth slice. So what we do is we take a, let's say, depth slice of the iso volume that we have, and then we just extract its boundary. Okay, and this boundary has multiple components, right? So we have colored them with different colors here, and we can see there are multiple boundaries. So these are for two different depth slices in same time step, and we can see the boundaries. Well, there are multiple components in them. Why components are important? Well, let's say we want to like track one of the boundary components. The another boundary component in same depth and same time step might not be close to it. We will have to consider as a separate surface front, right? So once we have these components of boundary, we extract the ones which are facing north. For that, we basically just start with the uh, westmost point, and we take a walk going north towards the eastmost point, and we collect the points which are there. So we can see here in example that this boundary front and this boundary front, it has something on the south side also. But when we extract them, we have only the one that's facing north. So we just take the east-west and westmost point and just take a walk towards north. Once we have these boundary fronts, we just collect them together, stitch them together to get a surface which is facing north. Okay, so this is basically our surface front now. Surface that's facing north and is boundary of the high salinity core. We extract these over each and every time step, and then we want to create correspondences between two surface fronts. Okay, for our edges, for our tracking. So that correspondence is created using the neighborhood that I just explained. So let's say we have a point P in a surface front I in time step T. We check in time T plus 1 if the neighborhood of that point P, right, interacts with another point in another surface front that's basically part of another surface front in next time step. So when we see something like this, we call this a correspondence, where it can be either a merge of surface front or a split of surface front, or a surface front might just be continuing forward in the time dimension, right? So once we have these correspondences, we create a track graph. Okay, so here the set of vertices or the set of nodes here is surface fronts. Each surface front is considered as a node, and each correspondence we track collected over time is considered as a edge over time. We can see that this is going to be directed a cyclic graph because we have only one directional edges going from time sub t to t plus 1. And to embed it in three-dimensional space to visualize it, we basically take a point point from a surface front which is closest to the centroid of that surface front. The surface front will have a collection of points. We take the centroid and we take a point which is closest to it in the surface front. So that we just use to embed it in 3D, and we draw edges as straight lines between these centroids, and we basically get a 3D visualization. So we use ParaView to visualize this track graph, and we can extract interesting tracks out of it to analyze how the HSC is moving. So this is the whole track graph that we got, and I have highlighted one track here just to show something interesting here. So when we extract tracks out of this track graph, we see a few uh, interesting things. So one thing we see is we get a group of tracks that basically moves towards the coast of Visakhapatnam, right? We also get another group of tracks which basically go towards the middle of bay and kind of stops there. And we get another group of tracks which is basically turning towards Andaman Nicobar, right? So this three this split that we see in our high salinity core, well, when we look at the existing studies of how SMC behaves when it enters Bay of Bengal, this shows similar behavior. SMC after entering Bay of Bengal is known to split into three directions, which moves the same way. So this helps us validate our results also, because it uh, is similar to what existing studies show. We see something which is not recorded in any of the existing studies. We see a track which starts at somewhere near coast of Visakhapatnam and tries to move towards the coast of Bay of Bengal. So this is high salinity water that we see, which is something interesting that was not there in any existing study. So this shows how high salinity water splits into different directions and gets mixed throughout the Bay of Bengal over time. Okay. Once we had these results, our next challenge was, so these basically show how high salinity core distributes salinity over Bay of Bengal. But we didn't exactly know what is causing all this, right? Why this what is the major force behind it? It could be mixing, it could be happening due to currents, or it could just be diffusion, right? So we started by looking at advection, which is basically the movement due to currents, right? So the advection is defined as uh, transport of materials or solutes due to the movement in fluid here, which is a water mass, right? And it's calculated as a dot product between delta of the uh, gradient of the field you want to, scalar field you want to study, with the velocity vector. So this is basically comes from a continuous, like this definition comes from a continuous system. We need to find, for discrete data, we would need to find these gradients over discrete data, and these are just the formulas for them. Okay. We can find the gradients over discrete data using these formulas. Now, we want to do something similar. We want to see how the high salinity core moves due to advection. So we focus on, here we focus on 35 plus minus epsilon PSU. So instead of focusing on like the whole iso volume and trying to again track that, we thought of looking at just the boundary which is near to that boundary that we had computed. So that's that has values around 35. So this gives us a layer of data from which we can extract advection points that we call. We can extract we can calculate advection and get clusters of points that are moving where the salt is moving due to advection and then track it over time, right? So the method is, well, goes like this. We again take that 35 plus minus epsilon isovolume on each depth slice, and we calculate advection for it. So after we calculate advection, we calculate something we call advection ratio, which is basically the ratio of advection to the total movement in salinity. Total movement in salinity, we want an absolute value, not the resultant value. So let's say the advection is bringing salt into a locality and it's moving out also due to some other reason. So the total would be get subtracted, right? But we want the total movement, either it's in or out. So we basically just take absolutes of the salinity movement due to advection and then the salinity movement without advection, and we add it up and we take the ratio with due to advection. So this gives us something we call advection ratio, and we put a threshold on it to collect a set of points which has very high advection. The threshold we use for our study is 0.95, so we want basically a point which has at least 95% advection, right? So once we have these points, we cluster these points using a neighborhood. This neighborhood is, well, a simple neighborhood of 5 by 5 by 5. This is not the same neighborhood we used earlier. This is just a simple 5 by 5 by 5 neighborhood, and we use it to cluster points into groups, and we call those points either advection cluster or advection front. So once we have these advection fronts, we just again want to find correspondences between two advection fronts to get an edge. We want to create a similar track graph, so we want to have correspondences. So here, for a point in advection front, we look at its velocity vector. Because we want to look at the motion due to currents, we just look at a velocity vector, and we see all the points that velocity vector can reach. If all the points that velocity vector can reach belong to another advection front in next time step, we say that there is a correspondence between them. We again consider these as edges and create another track graph. So same way, our advection fronts are now nodes and correspondences are edges. To get a three-dimensional point for our embedding, we again find the centroid of advection front and find the points closest to that centroid and just draw edges. The visualization is done in ParaView again, and we see something interesting, that the track graph that's given by just advection is very similar to what we had earlier, which was general movement of high salinity core. Once we extract the interesting edges tracks out of it, it becomes more clear. We have similar movements where we see salinity moving towards coast of Visakhapatnam and middle of Bay and towards Andaman due to just the advection. So, well, we ran comparison on the tracks after that. We even have a track going from Visakhapatnam up to the Bay of north of Bengal, north of the Bay. We ran comparisons on them because they were very similar. We did basically a distance comparison on both of them, and this shows that the distance between them, the maximum distance, so the distance between them we see comes down to somewhere between 90 kilometers to 115 kilometers, which is basically around a degree in Bay of Bengal. So 1 degree of a difference between two tracks, which is averaged over all of the track, is not a very large difference. This shows a strong correlation between the study done due to advection and the studies that we have done just using fronts. So the general movement of salinity and the movement due to advection is very similar to each other. This basically shows that the movement of salinity in Bay of Bengal is happening more or less due to advection, mostly. So from here point on, we tried to turn our methods into basically scalable methods where they can be used over very large data sets. The data sets we would be testing, we tested these on, were, like I said, we have one data set which is 1/12 of a degree over 200-meter depth and 122 times depth. To test how scalable our system can go, we basically resample it into basically 1/20th of a degree. So 10 times into lat, 10 times into long. So basically that would be 100 times the data size. So this is the data size that we have existing, and this is what we get when we resample it. So NetCDF is a compressed format, so we don't see 100 times size increase. Uh, we do a similar thing with a data set that we have, which is on 1/96th of a degree. There we want to downsample it to basically get a data set which 1/12th of a degree to compare our results as of how on two different data sets our system works. We can see here these data sets are pretty large, and this will only grow if we want to, let's say study over the rest of the planet, right? Let's say you want to study a bigger ocean region. This is just for Bay of Bengal. These data sets will only grow. So to understand how we implement it in parallel and fast, first I'll break down the whole front tracking algorithm into two major portions. One is where we compute boundary and surface fronts. Another one is where we compute edges, right? So for computing boundary fronts, we basically we store everything in form of a three-dimensional grid, and we just do a threshold on it to get any value that's greater than or equal to 35 and set all of them to 1, and the rest we set it to 0. Once we have this grid, we just run a 3x3 averaging filter on it, which should give us basically ones. So this is a 3x3 filter, right? So in a 3x3 grid, if all of them are ones, right, that's the only situation where it's going to be an interior point. If it's a point on the boundary, it will have at least 1 0 around it, right? So if the average gives us 1, that means it's an interior point and we don't need to worry about it. If average is below 1, that's a boundary point. And if the average is, well, exactly 1/9, it's an isolated point. So we ignore isolated points and the interior points, and we get the boundary. Okay. Once we have this boundary, we want to collect the boundary which is facing north. So that I already said, we take the eastmost point and the westmost point, and when we just walk towards the north, right? And we get our boundary which is facing north, right? Once we have all this, we want to club them into, well, surface fronts, and that like I said, we use a neighborhood for that to collect multiple uh, to connect multiple boundaries or multiple fronts into one. And for that, we just here use something where we spread those ones in the neighborhood that we want to look into, right? So let's say you have 2 points, and you want to see if they are in 70-kilometer neighborhood around each other. If you spread both those points to half of that neighborhood, right, they would connect. And if they don't connect, they shouldn't be in that 70-kilometer neighborhood, right? So we spread all the points by half of the neighborhood that we want to look at, and this gives us a simple neighborhood system where we can extract the points that belong to same neighborhood. Once we do that, so we even mark them with separate IDs. So here we can see we have marked this front that became a single neighborhood as 1, and the one which was away from it as 2. So this gives us unique identification for each surface front that we have. Once we have these surface fronts, now we need to do the edge computation, right? So edge computation is broken down into basically a simple mask. So we want to, let's say, look at edge in 70-kilometer radius. You pick up a 1 point from, which is a non-zero point from time step t, and you basically go to the same location in t+1 and extract basically the neighborhood that we want to look at. So we create a mask here, which is basically going to be of the size of neighborhood. Let's say you want to look at a neighborhood of 70-kilometer radius. Across it will become 140 kilometers, right? So this basically square will be a 140 kilometer by 140 kilometer square, and this mask has ones whichever falls under that 70-kilometer radius. Everything else is set to 0. So if we overlap this mask with the data centered around that point, well, we would get points which are set to 1 if they belong to that neighborhood, and everywhere else it will be set to 0. So from this resultant submatrix, we can extract the identities of surface fronts that we have correspondence to with this particular surface front from where we started, right? So this makes collection of edges pretty fast. How does this help us in faster computations? So like I said, everything we do is basically a grid computation now. Extracting edges, collecting surface, and we have broken down everything into grid computations. And we use NumPy for doing most of these calculations. And NumPy basically does direct addressing of each cell in the matrix, making it fast calculations. It doesn't have to serially go to each point. It can directly address each point and do the calculations. Also, NumPy is mostly implemented in C and Fortran using multi-threading, which makes each process parallel on its own and fast. We also, like I said, each computation is done on each time step. We need to only look at the next time step, so we can run for each time step parallelly. Because each time step has to look at only the next time step. We run all these parallelly using multiprocessing library, running basically, if you have 122 time steps, running 122 parallel threads or parallel processes to extract edges and surface fronts. So this makes our computations pretty fast. And this is, basically if you want to run it on a single machine, right? If you have very large data set where you have, let's say, 100 gigs of data, it's not practical to run it on a single machine. So we also wanted to create a system that can run on a distributed cluster. So for that, we use a similar implementation, just that instead of having it distribute using multiprocessing, we use OpenMPI to distribute our code over different cores of a distributed cluster. And we use a single procedure here also, which waits for the next time step procedure. So like I said, when we are doing surface front computation, we don't have to have any interaction between two nodes or between two processes. We only need to interact with the other processes once the surface front computation is done, because we need to look at the surface front from the next step. So this parallel threads, they will basically, after computing its surface front, they'll wait for the next thread to have done computing surface front. And once the surface front computation is done, it starts calculating edges. So the wait time is only a time step in t waits for t plus 1 only for computing a surface front. It won't wait for its edge computation or anything like that. Like I said, we use OpenMPI to schedule these processes over our cluster, and the NumPy parallelization we already get, and the time parallelization we do using this. We ran 3 experiments to see how scalable our system is. The first experiment is basically where we keep the number of time steps in the data set and the number of cores that we are using equal, and we increase both gradually. So in ideal situation, it should give us a constant runtime because we have same amount of resource with same amount of data. Again, we do another experiment where we increase the resolution of data, which increase the volume of data basically. And we see how the run times change with it if we have a fixed number of cores computing all that, right? We do another experiment where we basically flip that around. We keep the data size fixed and we increase the number of cores to see how that affects the computational time. For distributed computing experiments, we had this cluster which had 8 nodes. Each node is having 32 cores, 256 gigs of RAM. And for parallel computing, we ran it on a single system where we have, 2 CPUs attached to a single system as a single node, both with 128 cores. So we total have 256 cores on a single CPU with 1 TB of RAM total. Okay. So these are the results from our experiments. The first experiment where I said in ideal situation we should have a constant time. Here we see, so this is for the data set, the ROM's data set, where we had 1/96th of a degree resolution. And this is for the Glory data set. This goes to 240 time steps, this goes to 120 time steps. So the Glory data set, we have this upscaled it to 1/20th of a degree resolution. So this was around 80 gigs and this was around 75 gigs of data. As we increase the number of cores and number of time steps we want to compute over time, we see a slight increase We see the same thing in parallel computation also. But when we do parallel computation on our larger the ROMS dataset where we have to handle 240 cores, sorry, yeah, 240 parallel threads, we start seeing a spike after somewhere around this 176 parallel threads. I assume this is, I think this would be because, handling that many parallel threads is comes with its own overhead, right? Because when the number of threads are less, we don't see that spike, even if the data size is almost same. Here we have around 75 gigs and here we have around 80 gigs of data. We see the spike only when the number of threads is increased. So distributed system is better for handling large data sets when we have that many threads we are running. Okay, this is our second experiment where we plot the increase in volume of data with the time and keeping the number of cores fixed. We have so many plots here. Each one is for a fixed set of cores. So we can see like for the distributed system, we have, more or less linear structure. But for the ROMS dataset, we see spike in the end for all those graphs. And again, this uh, is due to basically us approaching the limit on the RAM that we have. So we had 256 gigs of RAM in each, and when this is stored in form of numpy arrays, it takes a lot of space. And this was approaching close to the RAM limit, and that caused this runtime spike. But up to then, until then, we see both of them are showing a linear increase. So with the linear increase in data volume, you get a linear increase in runtime. So we could basically say that it will scale well as long as you have enough resources. For the parallel computing, in again case of when you need a lot of threads, we see some like still it's close to linear, but we see some spikes here and there. And for parallel computing, when we have less threads to run, we again see more or less a similar linear behavior. For the third experiment, where we basically change the resolution, change the number of cores for a fixed resolution, we see that we have some runtime improvement over time, as we increase the number of cores, but that flattens after some time. And this is mostly, I guess, one of the reasons due to this, why this happens is we run them parallel over time steps. So if we have 122 time steps, we cannot give more cores than 122 because that's not going to be used. It will be wasteful. So the runtime improvement basically flattens after a while. Okay. We could, yeah, we'll talk about that later, I guess. So the last is basically where we present this fast implementation as a simple filter GUI filter on PyPyRocean. PyPyRocean is basically a system which, our team designed for visual analysis of ocean data. It's a collaborative effort. It's basically a plugin to ParaView. ParaView is just a general purpose visualization tool, and we create a plugin on it specifically for oceanography visualizations. This has many components, many functionalities, but with our work, we basically provide this front tracking visualization functionality to this. So I'll talk about that. This tool is again a collaborative effort and it's freely available to use. So this front tracking filter, basically once you have loaded the plugin, it just comes up as a filter in the options. You can use this. Then you have GUI to pass your input data file. Set a limit on what you want to limit it on. Like we use 35 greater than equal to 35. You can change it to 34 also, or whichever you want, right? And then you basically just press apply, and it extracts the tracks and give it to you. Again, this filter works with ParaView on a medium scale dataset, which is basically 1/12 of a degree, which is mostly used, and gives us basically tracks around time of 1 to 2 minutes, which is, can be used for an interactive visualization. Okay, so in conclusion, we provided two different methods that can be used for, tracking evolving methods over time. And we did validation for those methods using existing studies. We also showed some results that were, new. We also show that the movement of salinity, at least in Bay of Bengal, happens more or less due to advection, right? Other phenomena don't add much into that. We we see that there is some movement in the upper layers of Bay of Bengal, salinity movement, because we restrict our study to only 200-meter depth, which is, well, not that deep. Yeah. So yeah, I think, and also yeah, I'll talk about that here. Yeah. The computational methods that we present here, they are, well, highly parallelizable. And though we show only parallelism across time steps, because the calculations, like when I was explained, they are all independent for each depth slice, you could parallelize them across depth slices also to get even faster run times. We also provided a filter which can be used as a simple tool for the salinity analysis. It's not, again, fixed for Bay of Bengal. You could use it for salinity analysis anywhere in the space. For future work, like I said, we would like to show the case studies for both the methods on different data sets from ocean science or atmospheric science or some other field of science where we need to track some sort of scalar field. Because these methods don't fixate, the definitions are not fixated in oceanography, they should be able to adapt to any data set. Another thing is, like I said, about parallelism and scaling study. We would like to implement it, which is again parallel across depth also, so that we can use more resources to get faster results. And we would like to do scaling studies for that also. And yeah, that's it. Questions?